if there are no further questions, Shaker, can we move on to the next part of our presentation?
The next one is Marty.
Okay, Marty. Marty, please introduce yourself. You know, it's been a while since we met. I know I saw you at the last ISDC, or the year before. Please go ahead and tell us what you've been doing, and continue with your presentation, please.
Am I coming through good?
We can hear you. It could be a little louder.
Okay, I'll get a little closer here. Is that better?
Much better.
Okay, good. Okay, so my background actually is missiles and rockets and all that good stuff. And I moved to Las Vegas about 10 years ago. And a few years ago, I came in contact with a group here that was out to make a difference in nuclear. And fast forward these couple of years, I've become very involved in the group and do presentations with them, met some terrific people, met Dr. Craig Smith, who's going to be following this overview presentation. And so the big thing here in Nevada is, you've all heard of Yucca Mountain, I'm assuming. And with that circumstance that has gone on for many years with Yucca Mountain not being used, a lot of spent fuel is piled up around the country, and that has not been a good thing. As a matter of fact, there's more spent fuel now piled up around the country than there is room in Yucca Mountain for the amount of space that they'd have for it. So another solution needed to be found. So that's the focus of our group. So, but for focuses of today, I modified a past presentation and took it totally from the Earth-friendly perspective. And we have a rather bold title here. Nuclear is the only true renewable. And I put a big red whatever through wind and solar. And then the question that Craig discussed there a few minutes ago about small modular reactors, where we're all about this. And one other thing, when I'm addressing solar here, I'm not talking about specifically the solar panels you might have on your roof. I believe those are still a good thing. Nuclear is not here yet. To have backup power for your house is a great thing. What I'm talking about are these large fields that use the sun to generate power. And then, of course, the solar panels on your roof, they have a limited lifetime. And as I'll get into, their disposal is very difficult. They're not very earth-friendly. So this is why I'm bringing this up on Earth Day today. Nuclear has kind of got a bad rap by not being mentioned as a renewable, when really, as you'll see in this presentation, I and most likely everyone else on our team here in Nevada believes that it's the only true renewable. So that's the first page, and you'll be seeing this small modular reactor with microgrid graphic on a upcoming slide. So we'll get into that in pretty good detail. Just briefly, we're the Nevada Nuclear Science Consortium. So that's a group of us, maybe about 15 of us. And actually, we have a few members that are around the country. I'd like to acknowledge one that I know who's on. He's there in Minnesota, Steve Curtis. And there's others on the East Coast. But we're all working from Nevada perspective. Steve spent a long time in Nevada and was the focal point for the proposal that won the drone testing for Nevada. So, and he's got a background in nuclear also. So we have a great team of people. It's not just me. Okay, so on here, just a little comparison. This is kind of a little cartoon license, but basically, you can see all those windmills in order to put out the approximate 200 megawatt watts. It's not, it's pretty much, it's a cartoon with license, but basically showing you the comparison to put out that amount of power, and then to have a solar kind of field like we have at the border of Nevada and California when coming I-15 by the border Prim. Big solar field focusing on a tower. You can see what's required with land use. And then we have just representative, one small modular reactor does all this, and you can even bury them. So, so it's just kind of a rough feel for the efficiency, the energy density of what we're going to be talking about here. So I guess we're ready for the next slide. Okay, so this was a big revelation to me. Again, I'm kind of new to nuclear. Just came into this group about 1.5 years ago. So I learned a lot of things quick. I'd heard about Yucca Mountain, didn't know anything about it. I knew that they weren't moving fuel here, so my natural question was, well, what are they doing with it now? And I just never thought about it until that point. So this is a picture on the right showing what they're doing with it now. I don't know where this picture was taken, but as you can see on the map, the United States on the left, there's many sites around the nuclear, active nuclear power plants around the country. And I guarantee you that they have a scene similar to this and likely more material kind of piled up in their parking lot. So this is where the nuclear fuel sits because Yucca Mountain was never completed and opened. To say completed, that's an understatement, isn't even close. So my little summary here all around the country, nuclear waste originally intended for permanent storage in Yucca Mountain has been kept in casks behind chain link fences since about the 1970s. And yeah, generally in sight of the general public. So it kind of begs the question why they thought it was too dangerous to bury it in Yucca Mountain. But anyway, we're glad they didn't because we made a discovery about all this spent nuclear fuel. That discovery's on the top. It says spent nuclear fuel has only been depleted by about 3%. So about 97% of that is renewable, recyclable. It'd be kind of like having, here's my little camera, it has a couple little batteries in it, rechargeable batteries. Didn't know I'd be doing this. These rechargeable batteries, to not recycle this fuel would be kind of like taking these nice rechargeable batteries that I can recharge many, many times and throwing them away each time and just buying new rechargeable batteries and putting them in the camera. Really ridiculous. That's the situation we're in with the spent nuclear fuel. These are all rechargeable batteries, in essence, what you see in that picture on the right. Okay, next slide, please. And so why did this happen? It's probably that block on the right, the politics. That's what happened here. Little background, Yucca Mountain's about 90 miles up to the northwest of Las Vegas. You can see that little map. You can kind of make out Las Vegas down there towards the right and the little red dot up there, Yucca Mountain. There's an aerial photo of it. And so the original plan for Yucca Mountain was to build this array of storage space, tunnels, bring that spent fuel from around the country, put it in there, seal it up, forget about it. That's what never happened. Yucca Mountain has been in the courts for about 40 years. A lot of lawyers have made a lot of money on this on both sides. So now we have this problem, like I mentioned, all that spent fuel piled up. So what happened was, it was around under Jimmy Carter, he made a decision for the United States not to do recycling of spent nuclear fuel. And they have proliferation concerns. So anyway, that's a little background. And then with our leadership here in Nevada and Harry Reid and all that, it never went forward. Nevada put their foot down saying no. Federal government said yes. So anyway, in the meantime, the technology that we were focusing in on for the United States migrated out, and France really picked up the ball on this, and probably some other countries, and they highly advanced the spent nuclear fuel recycling art. And they have learned a lot, and I think the figure is about 70% that they're being powered in France by nuclear and using their spent fuel and recharging those batteries to do that. So that last picture there is aerial view. I don't know which recycling plant this is, but that's kind of what it looks like. Okay, so what we're talking about here is having Yucca Mountain, and this is just below the pictures, the new plan, temporarily store spent fuel in Yucca Mountain, just use it as a queuing area. Actually, since it's been sitting outdoors all this time, you wouldn't even need to put it in the mountain, but if we want to use the mountain, it is there, and it's in a nice area remote from Las Vegas to then build this, a recycling center adjacent to that area. Okay, next slide, please. Okay, so we're getting into this a little bit more. So you're going to say, well, what would you do with all that recycled fuel? We don't have proliferation kind of thoughts on that anymore. We say, wow, that spent nuclear fuel can be recycled and become the fuel source in many, many small modular nuclear reactors, which are really the paradigm shift for power for the country. Just my overview statement I like to say is that our use and need of electricity far outweighs the ability for it to be supplied in an assured manner. In other words, it's the grid, and you've all heard this, that question, what happens if the grid goes down? And there's lots of vulnerabilities with that. So, you know, we might be complaining about staying in our houses here for the past month in our own little biospheres. So just imagine if power went out for the month instead. Say there was none of this virus stuff, but the power had gone out everywhere. So picture, no refrigerator. You couldn't even recharge your cell phone anymore. The cell towers can't even function anymore because they can't get fuel into diesel generators, so forth and so on. Things would be in very bad shape. So this is an iterative process through small modular reactors to decentralize power distribution in the country and have assured power coming from thousands and thousands of small modular reactors, each being powered by the spent fuel that's sitting around the country now in all those casts. That's the big picture. Then each area has its own microgrid, which is built to specification for the level of robustness and resilience that you want it to be. And there's no limit. You know, these things, the concept is modular. They can be like very small, like whatever, a quarter of a megawatt or less. And Dr. Smith will have more details on that, or they can be put together to have hundreds of megawatt. Did I say milliwatt? I meant megawatt. Megawatts of power. So it's all what you need and what you would build out in a modular fashion. Finally, just a quick thing. To the right of the spent fuel recycling, there's a little picture that shows those little red discs on the floor. That 3% that is not recyclable, that's pretty toxic, radioactive. They've found a way to encapsulate it now. And this residue ceramic, encapsulating the residue in a ceramic kind of coating. And as you can see, there's a person walking on the floor in that building. Also, there could be a part in Yucca Mountain where that 3% is permanently stored. And I believe the half-life really gets reduced too with this recycling. So you wouldn't even have to bury it for millions of years. It might be 50 or 100 years. But again, Dr. Smith will have more details. Okay, next. Okay, so a little bit more just to familiarize yourself with this. This is our big thing here. The first reactor is going to be rolling out in about 2023, 24 or so. Our team here is working to get that tested here at the test site in Nevada. We'll see there's a couple of other sites, but we would like to test it here. We can do up to destructive testing here. We have a full plan for the reactors, for what you do with the spent fuel from the reactors. We can handle the whole deal here in Nevada. And we're also looking at not only temporarily storing the fuel in a queue so it can be put into recycling, but then we would like to attract and have Nevada be the small modular reactor manufacturing capital of the United States. So, but the bottom line of all this is we're phasing over dependence from the very vulnerable national grid. Power could go out in a second, or it might not go out at all. But if we don't begin this journey between now and 50 years from now, who knows what would happen. This is a phase-over process that would likely take about between 20 to 30 or 40 years to do. It's an iterative infrastructure process. Okay, next please. Okay, so getting back, it's kind of ironic, but nuclear has been a bad word in Nevada since the early 1980s. I just threw in this little picture here. If you're ever in Las Vegas, there's a real icon of history here. Atomic Liquors. It's on Fremont Street, just down the east on Fremont Street. Look it up on the internet. It's here since 1952, and people would come to Las Vegas to stand on the roof and watch the bombs explode. So there is a heritage of nuclear here, but it's been totally inverted. A very bad word. So this is working to reverse that, to see the potential of what this can do for Nevada, and especially, you know, the Strip. Who knows what's going to happen there? Are people going to come back here? This is a very proof industry. By the way, that nuclear recycling plant and those pictures I showed, that would cost about $25 billion to build. However, there's about $40 billion in this nuclear slush fund that could build it and have money left over, and then that just totally begins, ends the logjam for the country. So it's a great bar in Nevada, a lot of jobs in construction and operation, and then also perhaps we could have a national lab that springs out of it for energy, and also research and microgrids, the whole package. Small modular reactor evolution, we could all do it all here. Okay, and yeah, there's enough fuel. I don't know, I've heard from a few hundred years to 2,000 years, all this spent fuel. So I just picked kind of a number kind of low and in between. We for sure, or close to for sure, spent nuclear fuel to recycle to power the United States through all these small modular reactors for about 500 years. And probably within 100 years, we'll have like Mr. Fusion anyway. So anyway, this gets us to a very vulnerable interim place where we are, that we don't realize where we are, because the power usually comes on when we turn on that switch or we turn on the computer. But wow. It's not as robust as you think. Okay, next please. Okay, so and I'm going to wrap this up in just a few minutes. Have we kind of backed into this whole thing? Creech Air Force Base was a key thing for us. Creech is kind of on the way up to Yucca Mountain. It's about 40 miles to the northwest of Las Vegas. That's where they fly a lot of the drones that this country commands, flies overseas. And what happens, the pilot sits here and the drone flies there, which is on the other side of the world. It's called remote split operations. So in essence, Las Vegas and the ability to deliver power in Las Vegas is part of the weapon system. So how about that? We have this very secure, like, airplane flying around, unmanned vehicle flying around, or as they call remote piloted aircraft flying around in theater with missiles on it and doing military missions as we speak 24/7. Half of that weapon system is the power coming into Creech Air Force Base. So, and their power probably isn't as reliable as the power going to the casinos on the Strip. So put it that way. So Creech is very interested in having, they're kind of a leader in wanting to have their own small modular reactor. And one of the things with this reactor will be first tested out in a few years. If we test it up at the test site, there are existing power lines coming down to Creech from the test site that we can supply backup power. And of course, they still have their generators, whatever, but we can do some tests. And there might be periods of time when that reactor is just running and putting out power steady, and Creech can be receiving that as full backup power. So this is like the first step. We're really looking towards the military to be the initiator of this capability that will then, once proven safe and reliable, because again, this is going into the public, they see, oh, it's been operating for 10 years and the military loves it. And we've been rolling it out of airplanes in battle locations instead of trucking in fuel that gets blown up by the enemy. This is a very efficient way to have remote, like Army operations around the world or whichever service. So the military is going to prove this out, and then it will multiply from there. So that's kind of the first phase here is the military. So we're fortunate that Creech, right up the road, is very interested in this. We have the test site, and we want to get a small reactor getting tested up here as soon as possible. So we're working on that. Okay, so bottom line, if Creech can't fly their missions, you have national security, big national security problem. Okay, next, please. And so I'm going to talk a little bit, because this is Earth Day. Let's talk about the existing things. There's a few pictures and things I just kind of clipped off of some websites. 2.9 billion bird deaths are linked to solar and wind. So you got those big propellers. You have like these towers that's right near the border coming into Nevada, where you can see in that picture just below the bird, all those mirrors. The birds fly through that. It fries them. So very dangerous for both of these. They're not environmentally friendly. And you figure the logistics. You've seen these wind towers. It's like, imagine the concrete pad that you have to put in the ground to support that huge tower and those huge blades and the torque coming off of that thing. It's incredible. Not environmentally friendly. And then the wind turbine blades, they're 100% not recyclable. So here's a little picture. We bury them. So when those blades kind of finish their lifetime, like burying a bunch of styrofoam cups or worse. It's like, that's a huge problem. Solar panels, you can kind of recycle them, but there's a lot of different elements in there you have to separate out. It's a lot of energy to recycle those panels. With our nuclear approach, just bring on some more of that spent nuclear fuel and put it in that reactor. Those reactors are going to last a very long time. So, so it's a gold mine. All this spent nuclear fuel is a gold mine. This is the best thing that we could ever propose for Earth Day in terms of energy. Okay, next one, please. And there's been some articles about this even. So the most, if not all by now, green groups, they despise these towers. There's another picture there, the fields. Going back to my first slide, just recall, you don't have to go back to it again. Picture the amount of acreage that it takes to get a certain amount of power, or you could have something like the size of your house instead, providing all that power. That's what this article's about. And there's this little quote here, and they talk about how the whole thing can be put out triple the energy and 1/6 the space. So anyway, that was a great great article. So this is coming around, but still, as we speak, what are the renewables? Solar and wind. What about nuclear? No, what are you talking about? We're changing that. That's our mission. Very important. It's a great opportunity for Nevada and for the country and for the resiliency of our grid. And I think this the last one's my contact information. Go to that one. And then we'll get right into Craig's. Yeah, you have the last slide, Ken? Yeah, okay. So that's me. So you can read, we have a great website for, I should have put it on there actually. It's AIAA-Las-Vegas.org. Did I say it right? AIAA-Las-Vegas.org. Anyway, if you email me, I can get that to you. All this information's on there. And we have a lot of work to do and great group. And that's kind of about it. So we'll lead into Dr. Smith now. He has a whole level above mine of knowledge on this. He's a PhD in all these nuclear things. And he's going to dig in deeper. So all set.
Thanks, Marty. So I'll kick right off into this because I think time is getting short. My name is Craig Smith. A little bit of background. I received my PhD from UCLA, really more decades ago than I want to mention. I have had a career in a number of different areas. I was an officer in the U.S. Army for a period. I worked at Lawrence Livermore National Laboratory and also in private consulting industry. My last assignment at Lawrence Livermore Lab was as a chair professor at the Naval Postgraduate School in Monterey. And after a few years of doing that as a Livermore Lab representative, I retired and took a regular position at the Naval Postgraduate School. And that's where I'm currently working now. I'm here as a private individual. I'm not speaking on behalf of the Naval Postgraduate School or any of my prior employers, just to make that clear. But I do appreciate the invitation. We were sort of a last-minute entry, so I put together some view graph material that hopefully will complement what Marty had introduced and perhaps open the door for some questions and clarifications. Next slide. So this is a little bit of a repeat of the first slide that Marty showed, but with a little bit more detail. A couple of comments. The graphic, the cartoon is the same. I think one of the messages that you might take away from that is that from a land utilization standpoint, there's a huge advantage. Now, this comes from the simple fact that the fuel for a nuclear reactor is about 1 million times more dense in energy than other fossil fuels. And of course, that doesn't compare directly to the renewables that are shown here, but they do, wind and solar do require considerable land use. But it's not just land use. And this chart shows some of the other parameters that could be considered. So for example, the impact on wildlife, vulnerabilities to terrorism, life cycle threats, a number of years of utilization of the technology before you have to recycle that equipment. The availability, I mean, windmills are going to work fine while the wind is blowing. Likewise, solar plants will work well while the sun is shining. When it's not, you have to rely on energy storage. That adds expense and so on. The reactors that are shown in this particular picture are an advanced reactor that was developed in a program led by Lawrence Livermore Lab, and I was the lead there at the time. Now, this is 15 years or more older, and there are many newer small modular reactors that have been introduced since then that I'll talk a little bit about. So it's come a long way. But I would say that on that graphic, and Marty pointed out that it was some photoshopping done. Well, indeed, the only way you can see those reactors is that they've been blown up many times in contrast to the relative area that they occupy. But I think you get the point here. It isn't just land use, it's many other parameters as well. So the next slide, please. One of the important things to note, especially on Earth Day and especially in the context of this meeting, this event, is that nuclear energy is by far the largest producer of carbon dioxide emission-free electricity in the United States. And this Energy Information Administration graphic is a few years old, but it really hasn't changed very much. And at that point, 73% of the emission-free electricity generated in the US came from nuclear power plants. Hydro, a large second. The things we traditionally call renewables are pretty much down in the noise. And that's the situation as it is now. The numbers are probably a little bit different, but the basic message is the same. If you look at it on an international level, it's a similar picture, although hydroelectric is a more important contributor internationally, but the two, nuclear and hydro together, form the bulk of the non-CO2 releasing electric energy sources. So I think that's another dimension of what we're talking about here. Now, I would also say that I don't view the use, expanded use of nuclear energy and its potential to positively impact environmental considerations to be an exclusive argument. I think that much of the work that's been done, especially with small systems, has focused on how can you integrate nuclear power, small nuclear power, with other forms such as geothermal, wind, and solar. Next slide, please. So really that first chart the slide I showed was sort of beginning in the middle. And so let's go back to the beginning here. What is the trajectory that has brought us to the current state of nuclear energy development? Well, just a little bit of an overview of the history. Nuclear reactors were first introduced during the 1940s in the Manhattan Project. Following the end of the war and the successful development of nuclear weapons, the nuclear weapons, by the way, required at some point the development of the first nuclear reactors as a method for generating materials for the weapons program. But very rapidly after that, the Navy realized that ships could be powered by nuclear energy, and reactors for naval propulsion were developed. Then in the 50s, the Eisenhower Atoms for Peace program led to the commercialization and globalization, which was really a release of the Navy propulsion reactor technology into the commercialization world. Economics drove the designs to larger and larger sizes. And so there were 4 generations of reactor designs over the decades that I'll describe in a minute, with progressively reduced accident risk and improved safety. Of course, there was 3 Mile Island, Chernobyl, and Fukushima, each of which have been hiccups along the way. These all relate to reactors that are either obsolete, in the case of the Chernobyl reactor, or earlier generations in case of both 3 Mile Island and Daiichi, for earlier generations than what we're talking about here for advanced reactors and small and very small reactors that we expect to go forward in the next phase of nuclear energy. Next slide. So this is a real cartoon, and it's pretty fundamental. I think probably most of anyone on this call would be fully aware of it, that on the left side, you see the simplistic view. You have a vessel containing water, with fuel in it and control rods. You remove the control rods, you have a controlled nuclear fission process that releases heat, and the heat goes into the water and either directly or indirectly boils that water to produce steam, which on the right side, you see that whole power conversion cycle for what is typically a pressurized water reactor. And these represent the majority of the nuclear reactors that are operational in the world to provide electrical energy, something about 400 of them, of which about 100 are here in the United States. This chart, I think, is important for another point that I'd go back to before. The comment was made that with the molten salt reactor, you didn't need to worry about heat rejection or the use of water to remove the heat. Well, the reality is you do. You have to worry about that for any kind of power plant that produces energy in a thermal form. And if you look at the way the water circulates from the reactor into a secondary loop, within the secondary loop, there's a steam turbine, which is driven by the production of steam to generate electricity. But the steam then needs to go back into a condenser, and that condenser cools that steam back into the liquid state. But the way it cools that is by circulating water, cooling water, to remove what's known as waste heat, which could be 60 to 70% of the total amount of heat generated. And so that's true of any thermal generating plant. It doesn't matter whether it's coal, natural gas, oil, or nuclear power. You need to remove the rejection heat. Next slide. So coming back to the 4 generations of reactor development, they're shown on this chart with a rough timeline. And where we are now, we have a lot of generation 2 reactors operating. We have some generation 3 reactors running, and in general, the generation 3 reactors are the reactors that are newly being built now. Now, these are mostly large water-cooled reactors in which they're either pressurized so that the water stays in the liquid state throughout the primary cycle, or they're boiling water reactors, in which case the water is allowed to boil directly within the reactor vessel and produce the steam to produce electricity. Generation 3 plus is a sort of evolutionary design from these water-cooled reactors to improve economics for near-term and current level deployment. It's generation 4 that we get into new reactor concepts that are different in fundamental ways from the previous generations. The objectives are that they be highly economically efficient, that they represent enhanced safety, that they minimize waste and increase proliferation resistance. Those are generic objectives that need to be achieved, and they're achieved in different ways with the different kinds of reactor. So next slide, please. So these are the 6 types of reactors that are being considered in the Generation 4 program internationally. The first one's called a gas-cooled fast reactor. Then the very high temperature reactor, which is also gas-cooled but operates in a thermal spectrum. And just a very quick comment on what that means. A fast reactor is one in which the neutrons are allowed to retain their very, very high level of energy that they have when the fission takes place in the reactor fuel, and they're not slowed down. Thermal reactors are reactors in which the neutrons are deliberately slowed down by a slowing down material, which could be graphite or water, or in some cases other substances. And in that case, it makes it easier to produce a fission chain reaction to sustain it. But it also puts in creates some difficulties in fuel utilization, which is one of the reasons fast reactors are of great interest in the Generation 4 program. The third bullet here is the supercritical water-cooled reactor, which is really sort of the next level of water-cooled reactors. The bottom 3 are of particular interest. They're fast reactors in 2 of the 3 cases. And in the case of the molten salt reactor, they could be either fast or thermal, depending on the design. Sodium has been a liquid metal coolant that's been widely used for fast reactors for at least 40 years. The lead-cooled reactor is a newer concept that emerged from the Soviet naval propulsion program many, many years ago, but which has been sort of resurrected and has generated a lot more interest in the current advanced reactor development regime. And as an aside, I serve as the US representative for the Generation 4 International Forum with particular emphasis on the lead-cooled fast reactor. And then finally, the molten salt reactor is the sixth of these. So there are 6 different kinds of reactors. Their differences are fairly substantial from the existing water-cooled large reactors that we have, but they're basically opening the road for future of advanced reactors, some of which are small, some of which are large. Next slide, please. So I wanted to sort of reiterate that point with this very sort of elementary Venn diagram. On the left, you see the space of Generation 4 reactors. And on the right, you see Generation 3 reactors. And of course, they're not overlapping because they're different. But in between, the small modular reactors and very small modular reactors or micro-reactors are shown. And some of these are Generation 4, and some of them are Generation 3, and some of them don't fit into either of those categories. So, for example, the small modular reactor that was mentioned in an earlier talk was the NuScale reactor. And that's basically a pressurized water reactor, which is fundamentally Generation 3 type technology rather than Generation 4 technology. The reactor you saw in the cartoon at the beginning of this presentation, which is not actually being continued in development, but it's a conceptual design that's on the shelf. It was a reactor that was cooled by lead and is a representative technology in the Generation 4 program. So my point here is that small reactors can be Generation 3 or Generation 4. Advanced reactors are a different category. There's some overlap, but it's not a one-to-one correspondence. Generally, small modular reactors are reactors that are smaller than 300 megawatt electric in output. And they also enjoy modular construction. They have a lot of factory fabrication, and they include designs that are intended to simplify plant site activities that are required for final assembly of the plant. Very small modular reactors, or sometimes micro-reactors, are generally in the 1 to 50 megawatt range, usually smaller than 50. 30 megawatt is a more typical, perhaps upper level. But they're intended to provide even greater flexibility, such as full transportability, further improve safety and security, and they allow highly decentralized power production and integration into small microgrids that represent decentralized power opportunities or the opportunity to have dedicated power for critical facilities, which could be military, industrial, or government or other requirements for a small decentralized power production. Next slide, please. So these are a couple of summary graphics from Department of Energy describing their interest in and their perception of micro-reactors, small reactors with big potential. Plug-and-play reactors able to produce 1 to 20 megawatts to be used directly as heat or converted to electric power. They talk about small size, simple design, and fast on-site installation, and they show a cartoon graphic of a reactor being delivered by truck. So this is really just an effort to demonstrate the interest at the Department of Energy and to also kind of show what they have as their conceptualization of these very small reactors. Next slide. So the DOE perception of this, which I think is a pretty accurate description of what people working in the field are looking at. It's high levels of modularity, low capital investment, Now that lower capital investment may not be lower investment per kilowatt of installed capacity, but it'll be a lower total cost for a smaller plant, which has some strong economic advantages, particularly in economic risk of an investment. A large nuclear power plant these days could be many billions or even tens of billions of dollars. And for a small utility, that may be more than they could handle in their financial world. And so by going to smaller systems, you can get below some threshold where there's an interest in moving forward with an investment without betting the whole farm on it. There's siting flexibility, greater efficiency, and then safeguards and security is always a big concern, especially for the Department of Energy, and in particular non-proliferation. And economic development is a final bottom line for this. Next slide, please. And so getting to the idea of a microgrid, and also to make this the point again that I made before, that this is not necessarily a competition between small or advanced reactor technology and other renewables. And indeed, these small decentralized power grids, in many cases, cannot be successfully run with conventional renewables and need some other reliable power supply 24/7 to provide an anchor for the grid. But you can see here you have the idea of a potentially buried micro-reactor that is integrated into relatively small grid, which also integrates solar in this case, or wind, or both, and which could be also connected to the larger grid, but separable in cases of grid outage or larger catastrophic failure. Next slide, please. So just shifting to some of the kinds of reactor systems that are being considered. There's a half a dozen pictures of things that are being developed now. NuScale was talked about before. It's shown here on a rail car as a module. The General Atomics has a more compact but similar very small reactor concept, and as does Westinghouse, and that's shown on the pictures on the left. On the right at the bottom, there are two lead-cooled reactors that I'm very familiar with one being the one called Sealer, one being developed in Sweden with the intent of implementing it in Canada for remote locations. And it shows, at least in the cartoon, a picture of a man, so to get some idea of the size. The Holosgen and Hydromine concepts I'll talk about in the next couple slides before wrapping up. But these are just a small sample. There are many more under development. Next slide. So the Holos reactor is shown here. I think it's an interesting concept in the sense that you can see that it fits within a 20-foot shipping container. On this particular design, it consists of 4 modules which can be shipped together as a new reactor, and with a control rod or a poison material that maintains their subcriticality. When it's installed, the criticality that is achieved by these 4 subcritical modules comes from the linkage that takes place when they're moved close together. And so they become either critical or subcritical by the mechanical action of moving those modules either closer together or further apart. So this is a very interesting technology also, in that it makes use to the maximum extent possible of off-the-shelf commercially available equipment, and it actually operates a little bit like a jet engine. In this case, the picture shown is a single 20-foot ISO container, and that would be a reactor that would be generating in the 1 to 3 megawatt electric area. And if you had 4 of these 40-foot ISO containers, you would have a system that could generate 60 to 80 megawatt electric. The intent of this was for transportable, portable systems that could be deployed for the military to forward locations, operated at one location, and then relocated to a second location for continued operation. Next slide. This one, there's a company by the name of HydroMine that has developed an unusually compact, very long life, very small reactor, which is transportable in the upright position. And it's among the most compact power sources of any nuclear plant. It produces greater than 1 megawatt electric per cubic meter of the primary system volume. And it's passively safe with lead as the coolant. So there's a whole family of these which range from 5 megawatts up to 20 megawatts in size. And one of the applications being looked for this particular design is a ship propulsion application, which has the interesting feature that in the event of a catastrophic destruction of a ship that has this as its power supply, the coolant in this power supply would freeze. Lead will freeze very readily at environmental conditions, and thereby lock in all of the materials in the reactor core, all the radioactive materials, for subsequent recovery in the catastrophic case. So it's sort of a fail-safe design. It's an interesting concept that is currently under development. Next slide. So to wrap up, the work with Marty and the organization in Las Vegas, relates to achieving grid independence with a fixed or transportable micro power systems. Think giant battery. Think of a system that could be fueled for 20 to 30 years without being modified or refueled. Safe, sealed, pollution-free, reliable, and EMP and terrorist protected. And the application that Marty mentioned of Creech Air Force Base could be considered as a test site. And the need is pretty obvious there. So I think by now we're running pretty late on time. We'll go to the next slide. And I'll say thank you, and that'll conclude my presentation. Thank you.
Okay, thank you, Craig. A very informative set of slides. Now, if we have some questions, we are open to questions for all. For Marty, Craig. That was a long session, and when that happens, we sometimes lose our audience. But Craig, did you want to highlight on the reactors that are used in submarines? Now, if I remember right, we go back about 70 years, 1950s, when we introduced, I think, the USS Nautilus, was it? One of the early subs. And what generation do we use in modern submarines?
So we still use the pressurized water reactor, which is fundamentally an evolutionary series of improvements from the very early reactor types. Submarine reactors, and by the way, it's not just submarines, it's also the reactors that we use for aircraft carriers are fundamentally based on pressurized water reactor technology. And that is true also of the submarine and naval reactor technologies that other countries use, including Russia and some of our allies. Fundamentally, that's a very well-known and highly reliable technology that has served the military well. And the only exception to that, or at least the major one that I'm aware of, was a development in the 60s and 70s by the Soviet Union of a lead-cooled reactor, which was far more compact and put more power in a smaller volume than other reactors, and it was a mixed experience with the Russians, but that expertise has continued on. And it may well be that reactor technology leads to the very first actual construction of a Generation 4 reactor. Unfortunately, not in this country, but in Russia. But the naval power, ship propulsion reactor program has operated somewhat independently of the commercial industry, although the beginning of the commercial industry came out of that technology. The naval systems continue to be improved, continue to be evolved, but they are basically pressurized water systems.
We are talking hundreds of kilowatts of power, or
we're megawatts.
Megawatts, okay. Any other questions for Craig or for
Marty.
yeah, Marty?
Yeah, it's Marty. I think there is a question in Q&A.
Oh, let me see.
It's from Dr. Bradley.
Okay, go for it. Let me. How is it protected against terrorists? A good question. I thought there was one bullet in your slides that talked about underground. Go for it.
Yes, well, undergrounding is certainly one of the possibilities. I think you also have to realize that nuclear power plants in general are extremely robust. And so, for example, there are specifications for containment buildings that must withstand very extreme conditions, such as airplane crash into the structure. Security is important around nuclear power plants, and it's implemented. So I think counterterrorism, is one of the features that's taken carefully into account. But in terms of the robustness of these systems, I think it's interesting to note that in the case of the accidents in Fukushima, there was an unprecedented earthquake that took place, and all of the nuclear reactors that were affected in that region were unaffected by or at least they were accommodated safely under the conditions of this unprecedented earthquake, and they were safely shut down. It wasn't until there was a tsunami on top of that, which created the situation of eliminating auxiliary power, that these reactors got into accident situation. So the robustness, though, of the reactor itself is very strong. If you get to smaller reactors, the physical dimensions being as small as they are, it makes it much more feasible and economical to put them underground and to protect them even greater that way.
Madhu, I think there's another question from Monica.
Okay.
So I see the question, and in a nutshell, the question has to do with how can, in the education environment and in the public education, how can we move forward to achieve better understanding and hopefully acceptance of nuclear energy? And I think that is it's a very good question, and it's one that's fundamental. One of the colleagues that Marty and I are working with on our projects, he may still be on this call, Steve Curtis, has been very, very active in promoting the public education. And I don't know, Marty, if you, Steve, if you're on, could you let me know?
I think Steve was on. Then let me see if I can.
Yeah, he may have dropped off, but I know Steve is very active in presentations to large groups and so on. Now, over the years, I made a practice to go to a high school in the Bay Area, close to where I lived and worked, to meet with their chemistry, physics, and AP classes for a day every year to make some presentations. And I found that they went over very, very well. Students were interested. The teachers were also interested and found themselves to be educated. It's limited what one person can do, but the American Nuclear Society has a very active program for teacher education and for providing teachers with educational material that they can use in their classes. It's a very important question. It's a very difficult one. I don't know what the ultimate answer is, but I think we all have to work harder towards public education.
Steve is on board. I don't know if he's still there. There's no video, but I think his audio should work.
Steve, are you with us?
Yeah.
I'll try calling him.
Mr. Curtis? Hello? I heard he said something. Steve? Okay, I think he's on.
Yeah, I don't hear him, and I suspect he may be linked in, but perhaps stepped away.
You should hear me now.
Oh, there's Steve.
Good.
Yes, I had the other computer on. I don't have a microphone there.
Yeah, so Steve, the question was, what can we do for education in the school and in the public to improve the situation? I thought you might have some thoughts on that.
Yeah, that's a very good question, and I think the answer is that we could. There's two parts of that: education in the formal education system, and that's a matter of getting into the curriculum, which has been dropped from the curriculum for many years now, and that has to do with working with schools and working with the curriculum committees to get that back. But even a more important thing is education of the public. And I don't think there's any programs that are focused on that. That's where I've been focused, is trying to make presentations to different groups. And I think there's a lot of people out there that will talk about nuclear to groups. It's just there's not that many groups that want to listen. So if you want to schedule, if you find any groups that want to hear about this, we can find people to talk to them. And that's the basis of it. But people just don't understand, or they understand incorrectly, and that's the problem.
Yeah,
So I also believe that they have a strong group in Southern California of the American Nuclear Society. And these local sections have historically been strong promoters of teacher education and of providing educational materials, and also public education. So I think they have a strong role to play. I think there's a lot of work left to be done, and the professional societies ought to be a big part of that.
You let me know, I'll talk to any group you can find. And I think there's a lot of people like me. So that's, the long pole in the tent is finding people that want to sit down long enough to listen.
Yeah, that's great. Madhu, Professor Sangalvano is there. Well, I think, okay, there's okay, Monica said appreciate the answer. She said she will follow up and bring these resources to her school. Monica is actually Los Angeles County School District. She's like a STEAM director in the area.
I will say there's a lot of assets on the American Nuclear Society webpage for teachers. There's a lot of, if you go onto the education portion of the American Nuclear Society website, they have a lot of assets that can help teachers in the classroom, and I would suggest you do that. That's something you want to look into. It's ans.org.
Thank you, Craig. In other parts of the world, particularly in France, they bus students to nuclear facilities to see how clean and well run they are. I'm sure you're familiar with that mechanism of how students are told that that nuclear power is not only an option, but it's a very clean power production method.
Well, it's true that public acceptance of nuclear energy in France is very strong. It may have weakened a little bit, but it's always been very strong. But even here in the United States, in the past, the major nuclear power plants have maintained visitor centers, which are really wonderful points of education. I do know that immediately following the 9/11 incident, that access to those kinds of facilities became much more restricted. I know I was on a sabbatical teaching in France at about that time, and I had a couple of students who needed to collect some information on nuclear reactor design, and I sent them over to the nearest nuclear power plant, and they couldn't get in because of the security measures. So things have changed. It's got a little bit more difficult since then. But honestly, there's a lot of information that's available online. There's a lot of negative information, and that's also out there. So you have to be perceptive and discriminating in it. But I think in general, the American Nuclear Society has been very strong, both at the national level and the local level, in supporting things like student scholarships and education material for teachers. And I think if you talk to the chairman or program chairman of the local section, whether it's in Los Angeles or wherever, you'll definitely get a good response with with actual interaction, conversation, and hopefully speakers provided and so on.
This is very true, and children more than anybody else like the real thing. Craig, you know that they appreciate real things as opposed to PowerPoint slides. So anything we can do to bring them close to clean nuclear power may be one way to do this.
Yeah, I will reiterate Steve's comment there that there could be curriculum related issues here.
Yes.
That should be worked at a higher level. But it just seems, patently obvious to kind of close the circle on this, that renewability and recycling are characteristics that are environmental friendly. And that's what we've been talking about here. And it's really been more a political issue as to not include nuclear energy as a renewable source of energy. And I would point out that geothermal energy, for example, is a form of nuclear energy, and yet it's considered part of the renewable portfolio. So should nuclear energy be, if we want to make positive contributions in energy production without the carbon generation.
A lot of it has to do with the government leadership also. And Canada is very favorable because of that. France is very favorable because of that. Russia, China are all favorable because of that. Our government of late has not been very favorable to it, but it's changing. This administration seems to take more of an interest in it. So it's time to jump on board and learn about this if you guys all think it's a good idea.
Great. Any other questions from anybody, including our distinguished panel?
I just have a comment. It's almost kind of ironic. Everything we're doing is nuclear powered. That reactor is about 93 million miles away, and we interface to it with solar panels and whatever, or the movement and convection of the earth, whatever. But all this stuff that gets us power is really as a result of a large nuclear reactor that's far away. But that's the bottom line. We're powered by nuclear.
Yeah,
If you trace it back, it's coming from a big nuclear power source in the sky.
That is true, Marty. it's granted, but nobody wants to talk about it.
Right, but it's what powers everything. And we
This
have
is
these
true.
kind of inefficient coupling devices or interface devices between it and our lives. But, you know, the plants work very efficiently with that, and, you know, our solar panels. But what we're talking about here is recreating that capability, having your own kind of sun, so to speak, in your neighborhood to power you locally very efficiently. So, because we have this thing called electricity now. 150 years ago, we didn't worry about electricity because we didn't have it. So, but now that we have it, and very much we depend on it, as probably close as much as we depend on oxygen now. So, but oxygen's pretty much being supplied reliably and efficiently and robustly, but the electricity sure isn't. So that's what we're all about here, is to provide that robustness and efficiency, and having your own little nuclear source close by, at least as we sit here today, is the best we can do to do that. It's certainly better than the system that we have in place now. So it's an evolutionary process. But
It's interesting to know. Oh, go ahead. It's interesting to note also that, oh, I'm sorry. I thought you.
I just add a final thought.
Okay, go ahead.
Think about it like driving around without a spare tire. That's what we're doing with electricity now. We have no spare tire. We have no backup. Yeah, we all have little generators, maybe. We can siphon the gas out of our car for them. But in a week, everything stops. So this is the thing. This is very important, very vulnerable. And the small modular reactor microgrid concept, nothing's perfect, but it's up there in the high 90% of assurance of energy for as much as we depend on this stuff. Compared to right now, I'd put it in the low teens of reliability, really. It could be disrupted at any moment by any source of means. So think about it every day that your power comes on. It's like another day you're driving around without a spare tire, but you didn't get a flat tire. So, and especially on the 405 or something at rush hour. So that's the comparison here.
Thank you, Marty. Stephen, did you have something to
Just
say?
one little quick point. It's not something people don't know a lot about. You talked about accidents in reactors, but the nuclear industry has the best industrial safety record of all energy generation, including wind and solar, in the country and in the world, actually. And if you take all the accidents and add them all up, you find that there's almost every other business has a worse record than the nuclear industry. And ironically, it's the most overregulated industry in the world as well. And if we really want to have the future Marty talked about, we really need to start influencing that sort of a system. That's just an observation.
Thank you, Kip. I see one question again appearing, a question here from Casey. What is the possibility of someone developing a nuclear reactor in their garage for malicious intent? Oh my.
I would say zero. We can talk about that for hours, but I would not sit up nights worrying about that.
But thinking
Greg?
about it, I don't know if all of you are familiar with Joe Pelton's Handbook of Cosmic Hazards. It's an expensive book, but in which he mentions that an anomalously large coronal mass ejection event can shut out our existing grid, and it is something that has happened in the past before we grew up to be what we are with our satellites and so on, but can do tremendous damage. I mean, we don't have to go to EMP from other sources, but things like that can happen naturally. And so, good idea to a good idea to be thinking of shielding ourselves before things like that happen. Anyhow, it's past 3 o'clock. Shaker and Ken, is it time to wrap up?
Shaker, are you online? Oh, yeah, I think Shaker is probably offline. Okay.
Okay.
Yeah, so yeah.
Ken, would you like to close up? I know I thoroughly appreciate the discussions and the talks. Thank you all for literally volunteering your time, because time is precious, and it's wonderful to hear all of the various angles. That's what makes AIAA precious, and I hope to see you all at another meeting. I suspect it'll be many more. I heard the new term meetings, as virtual meetings, meetings. So with that, I will hand it over to Ken and to close. Thank you to Ken for doing all the hard work, because these kinds of programs don't happen without many email exchanges. And thank you all. Enjoy the rest of your afternoon if you're in the Southern California area, or good night. We'll be talking soon. Bye.
Yeah, thank you. Yeah, thank you, Charles. Thank you. Yeah, please look up to future AIAA event. Thank you so much. Thank you, everyone. Appreciate it.
Thanks, Ken. Awesome.
Yeah, thank you. Awesome.
Thank you.
Thank you.
Thank you so much.